Okay, hello, welcome back to another one of my video log recording sessions where I talk about genetic algorithms. Well, it's actually only one genetic algorithm so far, so I should just say where I talk about genetic algorithm, singular, not plural. But anyway, who's counting? Who's actually literally counting? As far as I know, no one except me, I guess. So, yeah, whatever. The date time is 2025 June 22nd. The time is 23:21 or 21 past 11 p.m. And yeah, so tonight I won't actually be covering a lot in terms of maybe in concepts or theories or just my speculations, whatever. I'm saying whatever too much, aren't I? I've already said it 2 or 3 times in the last 90 seconds. So anyway, whatever, those are kind of the same. So back on track. So I won't be covering that much in terms of concepts or ideas, advanced concepts or ideas, but I'll start with some a lot more well-known concepts or a way to solve a problem, that is the knapsack problem, and I'll continue on from there, which I think I'll mostly be just mumbling and ranting, just spitting ideas, trying to justify my last 5 to 6 months that I have spent in doing this. But the whole point of this series of video logs is, or was, or has been, for me to be honest and transparent about the whole process of developing these ideas and coming up with a better way or a more suitable way to apply this to the things that I would like to give birth to in the future. So yeah, I thought this vlog session is still quite necessary. Yeah, well, for the sake of being honest and transparent, I guess. But I will still try to justify my own approach, so stay tuned, I guess. I don't know. So for the last several months, this whole idea of trying to select the right items or trying to make the appropriate or the just right delegations of genes, given some conditions, some constraints, some parameters and some hyperparameters as well, and trying to come up with the best solution. Again, the phrase best solution is, or should be in quotes, but anyway, can be called as the knapsack problem. It is the knapsack problem where only a certain number of items, certain number of only a certain set, I should say, of items can fit into a knapsack. I think that knapsack is kind of too old, that word, so let's just say a backpack, because everyone carries around a backpack these days. Knapsack, I'll do that. Okay, and well, and usually only a certain set of items can fit into the said backpack, because it can only hold up to a certain weight, or more in general, constraint. So here and for the last several months, what I've been doing is the genetic algorithm, and and it is called such because the items can be the word items, or the word item or items can be substituted with the word gene or genes. I should also do that there. And weight could be, well, as I've already written here, typed here, can be called a constraint. I don't know how to spell, do I? Constraint. Or cost, depending on the situation. And for every item or gene, there will be a benefit or a utility value. Then this could be called a constraint value. Oh, yeah. And on and on and on and on and on and on and on, something like that. So that's seriously? Oh my god. Where did it all go? Oh, my bad. Let me do that again. Constraint, knapsack, problem, and sometimes I would just like to call it a backpack, because that's more common these days. And you pick items or genes, and they all have some utility values or benefit, or maybe profit, or just in general utility value for the cost of some weight, because you are putting items into a backpack, so that's a physical weight, or a constraint value, and on and on and on. Yeah, and the reason why what I have been doing was called genetic algorithm, genetic algo, is that the reason is, well, this word, genes, because every gene or every item could be represented in zeros or ones. It's like genes. So this and I guess people have come up with this whole concept of genetic algorithm because well, people didn't want to many brilliant-minded scientists, computer scientists or geniuses, didn't want to brute force anything. Brute force is bad. Well, is it bad? Sometimes it is. Most of the times it is. But for smaller smaller number, good, or just simple, no headache. So they didn't want to brute force the whole thing, especially when there were more than like 50 items, because 50 items, if you had 50 items, you would have, for 10 items, you have 2 to the power of 10 possibilities. So for 50 items, you have 2 to the power of 50, which is 1024 to the power of 5, which is approximately 000, 000, 000, 000, 000, 000, 000, and 000. That. So that's billion, trillion, quadrillion, 1 quadrillion possibilities. So again, that's a lot to think of, even when you are using a good computer. So they came up, I guess some people came up with the idea of using evolution and genetically, a way to a genetic expression to let me rephrase that. A way to express the different combinations in a genetical way. I wonder if I phrased that right, but anyway, that's what I'm going with for now. But it turns out that there are a couple of more ways to do this. Number one is the greedy way. I should write that here as well. There is the genetic algorithm, and another one is the greedy way, or the greedy approach. This is where you calculate the ratio of utility value for an item by dividing the utility value by the constraint value, CRNT, as I have always denoted them, and you just line them up, and then you just take the most, you just sort them in from the highest efficiency to the lowest efficiency, and you'd start taking from the highest one until you have hit, or you have almost hit, the maximum constraint. So that's one way of doing it. Another way of doing this is the what's it called? The 0-1 way, or the dynamic way. For that, oh my god. For that, I'll just type it 0-1 way, or the dynamic way. And this, as I've said in my last video, this is not to be confused with what I call the dynamic genetic algorithm, because these two mean totally different things. The dynamic word, the word dynamic here, refers to the concept of dynamic programming, whereas the word dynamic here, I meant that the hyperparameters are dynamic, as they would or can or should be changing from time to time. So hence the word dynamic. So totally different. Maybe I should be careful about how I name things in the future. But for now, just I should keep in mind that these two mean different things. Oh, okay. Just for the record, I'll just do this and this. It's no, they're not the same. They're never the same things. Okay? Please get rid of this. Thank you. Dynamic programming. So, this for this I would love to go through the couple or the several concepts behind how you try to solve the knapsack problem. I should write that. How you solve the knapsack problem. But I fear that maybe it will either take too much time, or I don't think I may have understood the whole thing entirely. I think I can, but for now that's not the focus of this video, so I'll just be honest. I don't want to cover this right now, but I can, just for the record, I can just leave a link. I can show what the reference that I used, what the code that I used, even where I copied the code from. It is from a YouTube channel by this wonderful expert called Neural 9. Here is his here's the video that I used and watched, and during my video log session I'll also try to record the code that I copied from his video, so that you can also, anyone watching this can also try. I just want to mention and emphasize that the part where I do the greedy approach and the dynamic programming approach, those source code, or just the code in general, do not belong to me. I saw it from Neural 9, from this video, so he explains things in the most crisp way that anyone could need while trying to quickly build something because they want to test something, test a concept. So please go check him out. Okay, great stuff. I'll also leave the link to this URL in my video. I should do that. Yeah, that's about it. So anyway, back to the code. So here's the code. So right now what I'll be doing is I decided to implement the two approaches from the video by Neural 9. Of course, the actual concepts themselves do not belong to him. They weren't created by him, but he implemented them nicely enough for anyone to just see the video and copy. So and maybe apply the code to however one may need to, to your own needs. So that's what I did. So there's the link again, by Neural 9. So what I did is make the list of 100 items again, preset items, and preset values, and preset utility values and preset constraint values, and prepare them into a dictionary as Neural 9 set things up. I didn't want to make any largely unnecessary modifications to the code or to the data structures that were being used in the code. So that's this part, and here is the greedy way, the code for the knapsack greedy solution. I'll just zoom in so that it gets recorded here. I'll just give 5 to 10 seconds so that anyone who wants to copy the code can actually copy the code. So that's it. Yep. And that's how you implement it. Until 10 items, until 20 items, until 50, until 90, until 100. And you do have to specify the max constraint, as in the capacity of the backpack. And when I do this, one thing that was interesting was that despite all the effort that I put into doing the entire problem in the genetic way, one of the very most simple, one of the very most basic approaches to this problem managed to solve it within some microseconds or milliseconds. So that's a huge letdown, isn't it? It's not, you know, I shouldn't be happy about it. But anyway, the truth is, it managed to get 2865 with the summed constraint value of 17940. So that's again one of the true ceilings. So that's that. Here is the dynamic way of doing things. Here's the code. Let me just yep. I'm only just pausing here because at the URL by Neural 9, there isn't actually a GitHub page or any file for source code. So this is like my homage to Neural 9's work. So this code does not belong to me, it belongs to Neural 9 by Neural 9. Okay, not my code. So that's the first part of the code. Here's the rest of the code. So what this does basically is it makes a table of how the items could be allotted depending on what the max constraint is from 0 to the actual max constraint that is set for 100 items, which is 18,000 for this case, because I have set that to 18,000 as I believe it's max constraint here. These are the lower max constraints that I have used so far for the 100 preset items. So the last value, which is for 100 items, is 18,000. And if we come back to the code at hand for the knapsack dynamic, here's the rest of the code. 5, 4, 3, 2, 1. Okay, moving on. Here are the max constraints, or a list of max constraints, from 10 items, 20, 30 items, 40 items, 50 items, 60 items, 70 items, 80 items, 90 items, and 100 items. And if I do this for every 10 items, for every 10 added items, I do get the right values, which is 2865, and all this can be done in 0.276 seconds, which is, I mean, suppose this is like 0.3 seconds. The shortest time that I've had was 38 seconds. So this is a lot faster. Yeah, like 0.3. Suppose it was 0.33, so that's 1/3 of a second. So that's 3 times 38. So that's 114, I guess. Yeah, 114 times faster. More than 114 times faster. And well, here's what the what this true ceiling chromosome looks like. But now, here I start the justification for what I've been doing. Let me zoom back out. If you remember, or have I not done this? I don't know. Let me just. Maybe I have. So, to refresh my own memory, I have a JSON file full of true ceilings, and in this notebook it says I have 220 known true ceilings when given these conditions, with the as in the max constraint value being 18,000 for 100 items from the preset values, from the for the 100 preset items and their values. As of now, I have 221 of them. I managed to, just out of pure luck, I managed to get just one more, which doesn't mean that 221 is actually all the possible true ceilings, as that's that I think is quite improbable, but I mean, it is how it is for now. So I have 221, but let's just say it's 220 for now, because it's only off by one true ceiling. So now, here's in my defense, it took 0.276 seconds, fastest 0.2 seconds, 0.2 seconds to come up with one true ceiling, which I believe, or which it was shown that was already in the all known true ceilings. So the quote unquote solution, I have to get back to this concept too. The quote unquote solution from DP or greedy and greedy were the solutions were already in the all known, or rather already known, true ceilings, which is kind of a bit retrospect. But then again, the thing is, for sure, the greedy approach will, no matter what we do, will always and only give us one solution, because of the way it works. It conditions everything in such a way that all the items are ordered or sorted from in descending order, from items that have the highest efficiency to the lowest efficiency. So it doesn't matter. So the order in which the items and their corresponding values are presented don't matter. The order, or the orders, the different orders they may be presented, don't matter, because no matter what happens, they will be ordered in descending order. They will be sorted in descending order. you know, in terms of their efficiency, in terms of their utility value to constraint value, util to constraint ratio. So there is only one possible solution that you could get from the greedy way. Now, for the dynamic programming approach, that is still kind of the same. You only get one solution from this, but that can be well, kind of fixed, not entirely, not 100% fixed, but that it can, I guess it can be worked around in a way by shuffling the order in which the items are introduced, like here. So I'm not actually going to run it here, I don't think I should, but if I uncomment this bit and activate it and run it, and run the knapsack function, run the knapsack dynamic again, run this again, it is there is a chance. I'm not sure if it's likely or not, because it's still 2 to the power of 100. The entire space is 2 to the power of 100 combinations. So it's not very likely, but it can happen. Well, getting a different solution or a different combination of genes or items is still possible, as opposed to what you would get if you just kept on running the knapsack dynamic function, this function, over and over again without altering the order in which the items are in. So if I do that, yeah, I'll be able to get some new ones, but for how long? Well, for example, if I wanted to get another one, no, actually, let's not do that. Just pure mathematics. If I had 100 items, no. If I had 100, I also need to take a sip. If I had 100 items from, I don't know. If I had 100 items, no, let's do this. If I had 5 items, namely A, B, C, D, E, the order in which these items can be arranged is what? 5. That. So it's 5 times 4 times 3 times 2 times 1, which is 120. So 5 factorial. If I had 100 items, it's I went ahead. If I had 100 items, it's 100 factorial. And let me just do a quick search. 100 items, 100 factorial is, oops, this number. So that's 157 zeros after 9. Do I have that right? Yeah. So that's a huge number. Well, let me see. 2 to the power of 100. Well, it is still less than this number, which is 2 to the power of 100. No, it's not. Shit. Sorry about that. It's still a lot more. So, well, that's embarrassing. I thought that was like 300. Now it's plus Now it's 30 zeros after. This is 157 zeros after 9. So this is still a lot. And not to mention some orders in which the items are sorted may give the same solution through the when using the dynamic programming way, when using the DP way. When using the DP way. So in order to find some other solutions, you have to do so many times of the DP approach, and without even a guarantee of hitting a jackpot or not. It could be a jackpot, it could be just one or two. Actually, one per DP approach, you only get one true ceiling. That's guaranteed. This is guaranteed, but if this is DP attempt 1, the very first one, and then you try another time by shuffling, by shuffling, which we will call DP2, you get another one. This is guaranteed, but whether or not these two solutions are different is not guaranteed. So you may end up doing from DP1 to DP98 and still end up getting the same solution, because per attempt you only get one. Okay, so that's one of the reasons why I think that's one of the things that I think the genetic algorithm approach has over the DP approach. I'll go Genal DP. So in a way, when done right, the genetic algorithm way guarantees more diversity, or let's just say higher diversity in terms of, and of course they have to, because this is kind of a given, because there are so many entities. It's not just one entity or one chromosome or one combination of items that we're looking at. For example, if I start with if I have 1,000 entities, I at least have a few hundred different ones, right? So of course it's more diverse. It goes without saying. And another reason for doing things the genetic way is, well, I've covered this idea or concept a few times, quite a lot of times actually. I don't like the word solution. I don't think I do, because it's very, it's quite human-centric. This is too H-centric, because the word solution implies that if it was me doing it, or if it was just us trying to optimize a problem, it means that we don't care. We don't care about other combinations. But why? Why should we not care? Why not? Well, because in the most conventional, the traditional sense, the reason these ¿por qué no? The reason this knapsack problem was proposed and studied and solved, again, solved, was that humans, us, or users, wanted a tool, or it could be a conceptual tool, because we're talking about the dynamic programming way of doing things, or we're talking about the genetic algorithmic way of doing things. So it's a conceptual tool, but which goes against the whole purpose of me diving into genetic algorithm. Because if something was to be truly genetic, or something was to truly mean anything resembling genetic, it shouldn't just end at finding the one bloody solution, because that's not, although I would like that to be the case, that's not how it is. That's as in, and by it I mean the world, or the universe, or maybe if someone is if someone is spiritual, that's not exactly how karma rolls, or that's not exactly how for some people God intends, because things change. And sometimes you need more than one quote-unquote solution. I'm getting good at writing with my mouse. Or maybe it shouldn't even be called a solution. It's just an entity, or it's just an entity with one of the few hundreds or millions of true ceilings. Of course, reaching the true ceiling or ceilings is very important. Reaching true ceiling is, vital. But creating the environment, the conditions, the atmosphere, to or for reaching the true ceiling is more important, or should be more valued, should be prioritized. And that's and you might say, oh, some people might say, but that's just not efficient. Then again, the core concept of genetic algorithm was that when you had a lot of items, when you had 100 items or 1,000 items, 200 items or 1,000 items, 300 items, whatever, the good enough answers. Oops. The notion was that they don't really have to be true ceilings. They don't really have to be true ceilings, but solutions just had to be close to the true ceilings, or good enough, right? Because they were just too costly to compute. Of course, dynamic programming may also just break when you have more than two things to consider when you have more than one constraint, one type of constraint, or more than one type of utility values. But anyway, genetic algorithm, the whole purpose was to find nearly the near true ceilings, or the quasi true ceilings, or the ones that were kind of good enough. So I am kind of continuing with that idea by saying that reaching true ceilings is important, but what should also be valued, and what should sometimes be more valued or viewed as more important, is creating the environment, conditions, atmosphere for and etc. for reaching the true ceilings when given enough time. Could be generations, could be era, could be a minute time step, but the potential to reach true ceiling. So this is more complex because it's got to do with the evo scheme, the procreation policy, the mutation, the learn method, the candidate method, what else? Oh yeah, the random or void entities, and all the other things, and maybe dynamic, or just in general, whatever. I should stop saying whatever. So this, ensuring that such environment, conditions, atmosphere, or policies are there in place for the entities to be able to reach true ceiling, or for some entities to be able to reach the true ceiling, is a lot more important, because things can change. The parameters can change, as in where is it? As in the utility values can change, the constraint values can change, or the hyperparameters themselves can change. Hyperparameters as in the number of items, or the number of entities, for example, or the mutation rate can change, or the not by a lot, but maybe sometimes yes by a lot, but it is a given fact that things do change and things can change. So I have to ensure that there is an environment or set, or a given set of the conditions given. The given set of conditions are, or do, guarantee somewhat of a robust population. Although the population in question may not actually have any entities that have reached the true ceiling yet, but the potential to do so have to be maintained, have to be there. The entities that can somehow be the true ceilings in the next 5 to 10 generations, or 5 to 10 time steps, have to be there. So that's the whole take, and that's I think that is the biggest reason why I should continue on with the genetic way of doing things. Yeah, because look at this. I have, 220, by now 221 true ceilings that all have 2865 summed utility values, and I also now know that this could be trivial, but I also now know that the bottle opener, camera, gun, and item 64, item 90, and item 91 are actually never used when trying to reach the true ceiling, which is amazing. But here's the funny story. Maybe it's not so funny. Interesting thing is that very recently I had to spend about an hour in the outside in the streets, because I had bought what did I buy? A bottle of beer. But I didn't actually have, guess what? I didn't have a bottle opener. So I guess I needed a bottle opener. But when I was coming up with these preset values, I thought, what good is a bottle opener? It's as opposed to, well, it's actually ranked quite high. Look, MacBook has a utility value of 100, and bottle opener has a utility value of 70, so it's quite high, right? And it has a constraint value of 300. Okay. But something changed here. These were somewhat arbitrary. When I was coming up with these preset values, you can kind of see that I thought that a bottle opener is quite important, because it had 70, whereas my MacBook laptop was 100, and when the laptop itself weighed about 1500 grams, somewhere around that, and I thought my bottle opener weighed about 300 grams. I could be wrong, but anyway, that's how I felt. And just take this as a story. Today I was out without my backpack, which had my bottle opener inside in the backpack, and I was without my backpack, so I didn't have my bottle opener. So maybe I should have recomputed well, maybe I should rethink about the importance of items that I should or would carry in person, on my physical self, maybe in my pocket as well. If I wanted to, live as a drunkard. But today I just felt like buying a bottle of beer, but I didn't have a bottle opener. So that's what I mean when I say conditions can change, and that's what I want the genetic algorithm that I'm trying to come up with to reflect. I want the evolution scheme and the policies to be able to cope with these changes. I know me going out and then buying some beer and not having a bottle opener to open it is a sudden change, but and it's not a grave situation in which 600 out of 1000 entities could just suddenly go poof and die. I know it's not, but those things may happen. Given enough time, those things can happen. And when that happens, the DP way, the dynamic programming way, or the greedy way, isn't just going to cut it. They're not going to be those methods or those approaches are not going to be able to provide us with somewhat of a diverse set of options, set of entities that can adjust to the new situations. So it's actually kind of okay if some entities or a lot of entities do not reach the true ceiling, as long as they are quite close to the true ceiling, or true ceilings, because there are 221 of them by now, right now. But that's the point. Effectiveness, efficiency, and robustness and diversity. These are very hard things to accomplish, to achieve all at once. But I believe if I'm not merely looking for solutions, that is the mindset I should have, because this is very human-centric, and the word solution indicates or implies that once the problem that for which the solution was sought after, once the problem is gone, the solution or the solutions don't matter, or the entities that are built on the solutions on certain combinations don't really, well, not really, but in a way they lose relevance. It takes away the meaning of existence. So I really don't like using the word solutions for this. But for the sake of explanation, I used the word. I mean, solutions is equivalent to true ceilings. I know that. But at least I have taken the time to discover 221 true ceilings. Trying to, kind of prove or trying to emphasize the importance of of a population being robust and diverse, because not because I want things to be diverse, because I want every entity or the population to be safe no matter what happens. I want the population to survive, and to do that the entities have to be somewhat prepared to anything, or to almost anything actually. And one of the ways of doing that is just compromising some efficiency and effectiveness for robustness and diversity. Oh, actually I have that here. So, and to do that, I'll keep using the genetic algorithm over dynamic programming. One thing that I can use the DP way for is if I have some new conditions, for example 1,000 items, whether they be generated or not, and therefore 1,000 utility values and 1,000 constraint values, then I can certainly use the DP, the dynamic programming way, to identify one of the many supposedly possible true ceilings, because this is a given for sure. So maybe I'll try the DP way 10 times, from DP1 to DP10, and if I'm lucky I'll get 2 true ceilings. But at least by doing this, I'll know what the true ceiling or true ceilings are, what the summed utility values of a true ceiling should be, regardless of whether they're different or not. whether the genes are different or not. So that's DPUA is a good way of doing that, and it's quite fast. So I should use this quite often from now on. Whether I do dynamic genetic algorithm or the one that I should be doing, which is chaotic genetic algorithm. But yeah, I can use that. Cool. That's about it. Thanks for watching. Bye. Okay, let me just zoom out. Have the whole thing recorded. Okay. Bye.